So let me know when we're good to go, and then we can get started.
Yep, we're good.
Okay, let's do it. So last time we were not there, we were here. So last we left off, I gave everyone a disclaimer, oh my God, so wild, about Drugs Lab, which is this amazing YouTube channel. Really, I just can't take my voice seriously like this. It's so high-pitched. Sorry. So this YouTube channel, Drugs Lab, is an awesome resource, really valuable. It has a lot of really interesting, I would say, videos of real live hot young Dutch people doing drugs on camera for your viewing pleasure. And if that's not your favorite kind of media, then I'm not sure what you're doing. But the one thing that I'll say about Drugs Lab is that it does contain sometimes kind of misleading or problematic harm reduction information. So if you're watching Drugs Lab videos, they are really informative, they are really interesting, they are really funny, but please make sure to also do your own harm reduction research. So when I show Drugs Lab videos, just know that that disclaimer is in place. And I'll probably say that a couple times in the future so people that didn't hear it the first time can get that information. So previously, we've been going over a couple of different neurotransmitters. I think we've looked at dopamine and dopamine and norepinephrine so far. So does anyone remember which category of drugs is predominantly impacted by dopamine and norepinephrine?
Stimulants.
Stimulants, thank you. And what does dopamine do as a neurotransmitter? What does dopamine do?
Reward system.
Yep. And what else?
I forget if that was if it was that or norepinephrine that makes you horny.
Oh.
It might be both.
You know, I'm actually not sure which of them contributes to libido more. That's I've never really thought about that. I'll look it up. And also there were questions that I didn't answer last time that I need to send a follow-up email about, so I'll make a note on those. But dopamine is also responsible for controlling motor control, right? And the reason that that's relevant is that in people that use chronic heavy doses of stimulants, particularly methamphetamine and just other stimulants that you're using high doses of regularly, you might start to see a deterioration of motor control because the neurons that are responsible for engaging in motor control may be damaged over the course of time. So interesting thing to keep in mind in terms of Parkinson's and Parkinsonian symptoms in drug use and stimulant use. And then norepinephrine does what?
Get up and go.
Yeah, it's your fight or flight system. So let's look at a new one now. And because, again, I love these icons, let's look at GABA. And GABA is, you know, it's an abbreviation for hey, y'all. Housemates, man, you know you love them. Can't live with them. Can't live without them. But mainly you can't live without them. So GABA is responsible for calming your system down after it's been hyped up, right? This is the chemical, the neurotransmitter in your brain where if you've been experiencing a swell of anxiety for something, then your brain will release GABA basically to bring you back down to baseline. So if you've, for instance, just like walked past someone that you swiped on Tinder and decided to avoid permanently, your body might release a little bit of norepinephrine in there and then, or a little bit of glutamate, whichever, and we'll get to glutamate in a second. And then once that rush is past and you're like, oh no, that's my Tinder swipe's doppelganger, then GABA might be released in your brain and your body will be calmed down again. So the class that primarily acts on GABA is depressants. And this is kind of a tricky one initially to wrap your head around because more GABA means you are less excited, you are calmer. So an increase in GABA will slow your system down. This is called inhibition. It's reducing the activity of your neurotransmitters. So that's important to remember with GABA is that if you see a GABA agonist, and I know it's been a minute since we talked about agonists and antagonists, so I'll reiterate what those are today. If you have a GABA agonist, that means that the effects of GABA are going to be increased, which means that you're going to be less active, or your brain is going to be less excited than it would be otherwise. If you have a GABA antagonist, it basically is hyping your system up. It's less calm in your system. That can get a little bit confusing. So depressants, generally speaking, will act on GABA, and they are GABA agonists. They increase the effects of a neurotransmitter that slows down your system, right? An inhibitory transmitter, a word that we'll come back to in a little bit. And this generally means that your central nervous system activity is going to be obviously depressed, right? It's going to be reduced across the board in activity. And some examples of depressants that we might see in particular that are prescribed and depressants. I don't have Prozac on here. I have no idea why Prozac is on here. You should ignore that. Maybe I should have looked at this. But benzos, for instance, Valium and Xanax are examples of clinically prescribed depressants. Excuse me. And then we have things like Lamictal, which is a mood stabilizer. And this is kind of an antipsychotic adjacent, if I remember correctly. But there are a lot of depressant medications that are prescribed, or medications that have depressant effects, which is why a lot of medications, particularly antipsychotics and anxiolytics, which reduce anxiety, might cause you to feel sleepy or drowsy.
I'm taking a combo of Lamictal and atypical antipsychotic for depression.
And does it make you drowsy?
It's supposed to.
It's supposed to. So here's a kid that's chugged some cough syrup at IHOP, just for fun.
My name is Joel, and I am outraged. I am pancakes at the International House of Pancakes. IHOP is what it is known as. It is known as IHOP because there are pancakes here that you can order for food. If you would like to order some pancakes, they're right here on the menu.
God, I love this kid. So that's, obviously everyone that's tripping balls on DXM is going to look slightly different, but depressants will slow you down just a little bit in multiple ways, or perhaps in some ways more than others. Now, serotonin, I'm sure, is a molecule that many of you are more familiar with than others, right? And serotonin is a really interesting one. It's a very scarce neurotransmitter in the brain. You don't have a lot of it to work with. And serotonin has a lot of roles that it plays, but you actually primarily see serotonin in the realm of psychedelics and MDMA, but the way that they work for psychedelics versus MDMA is very different. And we'll go into exactly how it's different. But this is an unusual neurotransmitter because altering the way that it works will change your perception of things. Releasing a lot of it will change your feelings about things. So it's a crazy chemical. We're still learning a lot about serotonin to this day. We still don't know a ton about it, generally speaking, because it's so complicated. But overall, it's a mood regulator. It helps with your sleep cycle, or it's important in your sleep cycle, and your hunger regulation. So generally speaking, for the sake of layman's terms and simplicity, we're going to say that if you have more serotonin, you have more pleasurable feelings and more sociable behavior. So serotonin is often released to make you, and dopamine in different ways, are released basically to reward you from doing things that are biologically satisfactory. With dopamine, a lot of this is in terms of like feeding behavior, for instance. You eat something, you have sex, you do something that's good, you get the feeling of being rewarded. You're like, oh yeah, that feels like satisfying. With serotonin, this is more along the drive to participate and be social, and like the pleasure that comes from engaging in activities. But it's very nuanced. There's a lot to be said about serotonin, but for our intents and purposes, we'll leave it at that. Now, psychedelics are different than what we've seen so far, stimulants and depressants, because unlike stimulants and depressants, whose predominant effects or a major part of their effects is speeding up or slowing down your system, psychedelics do not have notable central nervous system activity. So for instance, you might have a little bit of stimulation and that you feel awake when you wouldn't have otherwise, which is part of why microdosing psychedelics is very popular from a productivity standpoint in a working environment. But they're not going to make you feel speedy in the way that a stimulant would, and they're not going to make you feel drowsy in the way that a depressant would. So psychedelics are really kind of, please make sure to mute yourself. Thanks. Psychedelics are really interesting because some of them will just kind of bind at the serotonin receptor and just hang out. They just like pull it over its head like a blanket. That's what acid does. That's how LSD lasts 12 hours. Pulls the serotonin receptor over its head like a blanket and just fucking chills. Like watches Netflix, listens to Love Island narration, like whatever it wants to do in there. And that's how it exerts its effects. How exactly it does that, still getting there. As a quick intro to psychedelics with this amazing MS Paint drawing that I pulled from the internet. I'm not sure why I chose this one because it is absolutely unequivocally the ugliest that I could possibly have found, but I think that's probably why I chose it. This is a poor depiction of serotonin molecules. Remember, this is the axon terminal right here, the presynaptic neuron, right? And then down here we have the postsynaptic neuron and the receptors embedded in this postsynaptic neuron, the dendrites. So we're looking at the fingers down here and the foot up here. So when an electric signal comes through, we're going to see all these serotonin molecules released, or some of them at least released. They're going to bind at these receptors, and instead of the serotonin molecules binding at these receptors, if we introduce LSD into the system, it will sit itself fucking pretty right there, and it'll just lock in for a while. And that's why serotonin receptors can't bind. That's how this exerts its mind-altering effects. Now, one of the consequences of psychedelics is, and I love this graphic, I think this graphic is a really excellent depiction of what psychedelics do, is increased associations between things. So on the left, we see this kind of vague chart, which I should have sorted somewhere, or cited somewhere, so if you want the citation for this, let me know, I'll find it. But this was from a really interesting study about psychedelics and associations. So we see here that someone that is not under the influence of psychedelics, this is kind of like a neural representation, is having, like, there are associations being made in the brain, but generally speaking, there's a lot of calm. But as soon as you introduce psychedelics, specifically in this case psilocybin, into the mix, all of a sudden you have this massive web of connections being made within the brain, like areas of the brain that are communicating with each other that wouldn't have yet usually. And we've seen that certain psychedelics can actually stimulate the growth of neurons in the brain. Come way back to that, I can't get sidetracked here. So in case you've never been around someone on acid, you might think, and that's the reason that I have all these videos in here, is just to give you kind of a vague basic idea of what these categories of drugs might look like in one specific minor context. This is by no means generalization. I've seen people on MDMA that were like eyes rolling back in their head and like that, and like twisting their limbs all over, and I've seen people rolling that are just like smiling at you and like maybe going like this a little bit. So it really depends. But if you've never been around someone on acid, and you have the common misconception of like people on acid see pink hippos or whatever the fuck, and they're like going to be very obviously high, it might be more like,
what up, dudes? This video that you're about to watch, I actually filmed
this.
over a month ago when I was in Oregon. It's an LSD trip that I had.
Wow, it's just a stick, but look at the way the ice is like formed around it. Whoa.
That's it. You know, catch people on acid just like sitting outside their house staring at leaves for a while, being like, this is so cool. One time I had a friend who was trip sitting someone that was tripping really hard, and this guy was freaking out and nothing could calm him down. So my friend took him outside, and they noticed that they had a loose thread on their jeans. So they pulled it off and held it up and said, now I have 2 pairs of pants. And the guy was so flabbergasted by this that he just started cracking up and didn't stop for an hour. And that was it. He was fine the rest of the trip. He just like, that's insane. Like, that's ridiculous. Now, on a completely opposite end of the scale, this is MDA, which is another serotonergic drug that's very similar in a lot of ways to MDMA or Molly. MDA is kind of like a different preparation of a similar substance that tends to be more stimulating, more tactile, more psychedelic than MDMA, but they are quite similar. So sometimes it's used as an adulterant. So this is, again, the same neurotransmitter being acted on, but instead of augmenting the existing function of the neurotransmitter by sticking itself in the receptor and changing how the receptor functions for a while, this drug is releasing a bunch of serotonin. And you'll see how this is a very different experience, even though it's still just kidding, acting on the same neurotransmitter, right?
Zo fijn. Zou ik even kijken of ik wat energieker kan worden?
Wanneer ben je zin?
Want anders ga ik te veel in mezelf en te veel mellow. Ik denk dat je het goed kan sturen. Ik denk dat we nu een up-tempo nummertje aanzetten en lekker gaan dansen. Even bewegen. Ja, even bewegen. En even een beetje de energie erin.
Die moeten even op hoefpad.
Ja, op hoefpad. dit is gelijk een ander gevoel.
Ja?
Ja. Het is gelijk een ander gevoel.
I just love looking people roll. Whoops. Also, I just saw a brief note saying that this person here has assault allegations against them. So thank you very much for pointing that out to me, and I will swap out this video for something else. I'm not familiar with this person as a YouTuber, just of that specific video, but I appreciate the heads up. Also, as another heads up, if you need to reach me during class, I would advise that you email me, text me, or message me. Otherwise, I will open the message right here in the chat bubble. And if it's a private message, then I really have no way of knowing it until I've opened it. So just as a heads up for everyone. Okay, so glutamate, yet another neurotransmitter, right? This one in particular is responsible for facilitating communication between neurons. So glutamate is predominantly involved in communication and learning and memory in particular. And you can kind of probably figure out why glutamate would be involved in memory if it's responsible for facilitating communication between neurons, right? So we can extrapolate here that more glutamate activity means more communication between neurons, a heightened communication. Less glutamate activity means less communication between neurons. And I think actually glutamate is prominently connecting brain and spinal cord actually. So glutamate is a really big neurotransmitter that controls how your brain interacts with your body. And that's why, can anyone guess which class of drugs glutamate is involved in? Reducing glutamate might be involved in what class of drugs?
Depressants?
You're close.
Dissociatives?
Dissociatives. Nice, nice. And we're looking at the predominant class of drugs right now. You know, a lot of these neurotransmitters have actions on multiple classes of drugs, but right now we're just looking at the main class of drugs for each of them. So in the case of glutamate, this is the symbol that I'm going to use for dissociatives. The wine bottle is for depressants. I know this one is a little confusing because it also is a depressant, but you know, I can't really put like a bag of white powder and have it make sense. So glutamate, more glutamate is more communication between cells, less glutamate is less communication between cells. Okay, so dissociatives reduce glutamate activity, right? And this is going to be our symbol for glutamate for reasons unbeknownst to me. So dissociatives will, in many cases, reduce central nervous system activity, not in all cases. Like ketamine, for instance, like I said, will not depress your breathing quite as much. So some major dissociatives are ketamine and nitrous and PCP, which is making a little bit of a resurgence right now, and cough syrup, and there are a lot of like more minor dissociatives on the market, like 5-MeO-PCP, or no, 3-MeO-PCP, MXC, stuff like that. I guess we could go into this real quick, but don't worry if you're like, this is fucking actual Klingon, like I have no idea what you're saying right now. So the NMDA receptor, right? What we're gonna see a lot of the time in receptors is that a receptor is usually named after the neurotransmitter that it accepts, right? So a glutamate receptor, a serotonin receptor, they accept those neurotransmitters. But in some cases, we have specific receptors within that category. So a specific kind of serotonin receptor might be the 5-HT2A receptor, which sounds like gibberish, I know, but that's a specific receptor that serotonin will bind to and produce psychedelic effects. So if you go onto, again, a wiki page and you see that something has a 5-HT2A binding affinity, then you might look at it further and be like, is this part of a class of drugs that might exert some mildly psychedelic effects? And it might not be, but it's a good place to start. So within glutamate, there's a specific kind of receptor called the NMDA receptor. And I know that's really confusing because we have MDMA as well, but the way I remember it is fun to party with NMDA. And if you guys were unlucky enough to be in a classroom with me, I would make you all stand up and do that right now. And everyone hates it, but it's my favorite part of the entire year. So the NMDA song, remember it. The reason that it's important here is that pretty much all major dissociatives are specifically active at this receptor. So if you see that something is an NMDA receptor antagonist, I know it's a mouthful, but if something is an NMDA receptor antagonist, you immediately know by looking at NMDA, oh, that's a kind of specific glutamate receptor, which means that this drug is going to reduce communication between brain and body because it's an antagonist. So again, this is all intended to help you read scientific literature and be able to understand immediately what a drug's effects profile might be. So we see glutamate typically go in here, right? And that would unlock this receptor. And whoop, is there anything more to that? No, I guess not. So yeah, typically glutamate would bind to here and it would open the receptor. So question, and again, if you've been using your voice and speaking a lot during class so far, make sure that you like wait a couple seconds before answering. What does glutamate do? First question.
It reduces the amount of communication your brain gives out?
It reduces communication, or I'm sorry, not reduces. Glutamate as a neurotransmitter is responsible for facilitating communication, but you have the right idea with communication. Glutamate is a facilitator of communication. It increases the communication within your brain and with your brain and your body. So that leads to my next question, thank you, which is when it binds to this receptor, what happens? If glutamate, just glutamate, binds to the NMDA receptor, what happens? What's the effect? Might be simpler than you think.
Might learn better.
Might what?
Might learn stuff better.
Learn stuff better. Yeah, so NMDA, when glutamate is binding at this receptor normally, then it might facilitate communication within your brain and your body. That's all I'm getting at with that. What might an NMDA receptor antagonist do?
Make you dissociate.
Make you dissociate, right. So that's because you're reducing communication within the brain and between brain and body. It's an antagonist, which means that it makes that receptor do less of what it would normally. And in this case, the reason that that happens is that you're basically blocking signals from continuing to go through. So glutamate normally will continue signals through. That's its job. Glutamate makes signals go through. When you stop glutamate from doing its job, signals stop. Communication ends. That's why you feel dissociation from dissociatives. What class of, oh, well, I just responded to that. Class of drugs that is NMDA receptor antagonists is dissociatives, right? And if there's anything that you take away from this that's more important than the specific receptor, although it's good to understand specific receptors because it gives you a much better idea of what a drug does, is that glutamate is responsible for letting signals pass through and connect the brain and body. It's responsible for communication. And if you introduce a glutamate antagonist, then it will dissociate you because it's preventing that communication from taking place. Does everyone feel good about that? Any questions on that? Okay. So here's a horrible, scary diagram that I usually just skip because it's horrible and scary. And so we're going to actually do that right now. Cool. So I just want to cover something that is kind of a more terminological, is that even a word, thing, which is the difference between an inhibitory and an excitatory neurotransmitter. And this is different than a drug. If we're talking about drugs, a drug can be an agonist or an antagonist, which means that you're increasing or decreasing the effect of an existing neurotransmitter. When we're talking about neurotransmitters themselves and what they're already doing inside your brain, we're looking at two specific kinds of neurotransmitters right now. And there's one major inhibitory neurotransmitter and one major excitatory neurotransmitter. So an inhibitory neurotransmitter decreases system activity because it prevents signals from going through in the system. An excitatory neurotransmitter, and if you guys are not laughing at this GIF, then I don't know what I'm even here for, is a kind of neurotransmitter that causes an increase in system activity. I'll actually just let you guys know that last semester there was a girl in my class that laughed so hard at this GIF that we actually had to stop for a couple minutes because she just kept cracking up every time she thought about it. So if you aren't doing that, then I can't help you, honestly. So an inhibitory neurotransmitter, an example of this is GABA. So if you increase the effects of an inhibitory neurotransmitter, then you're going to have a full system reduce reduction of activity. If you decrease the effects of an excitatory neurotransmitter, then you're going to see an overall decrease in system activity, right? So I know this gets a little bit confusing because sometimes you'll see something like a GABA agonist or a GABA antagonist or a glutamate agonist or a glutamate antagonist, and you're like, okay, well, one of these things makes things go up and one of them makes things go down. So I just want to reiterate the difference between GABA and glutamate. And the other neurotransmitters have different effects. They're not excitatory or inhibitory. The purpose of GABA and glutamate is effectively to facilitate increasing the connection in your brain and body in the case of glutamate, and in the case of GABA, it's to facilitate decreasing communication within the brain and body, because that is responsible for making you feel calm after you've been hyped up again. I know that this is a lot of flip-flopping. Promise we'll go through it, make it seem more clear. So GABA is an inhibitory transmitter, right? So if you see more of GABA, it's going to inhibit the system more. Glutamate, excitatory neurotransmitter. If you see more of glutamate, it's going to excite the system more. Does anyone need clarification on that? I know that's a little bit confusing. The point that I want to make here is that GABA inhibits your system, glutamate increases / excites the activity of your system. And drugs that influence those will have sometimes kind of converse effects. Any questions on that? Any confusion? Let's watch someone do ketamine. Let's watch someone do a really large quantity of ketamine. I just want to make this clear. Usually you're not going to do this much ketamine and feel the way that this guy does. This is not a recreational dose of or like it is, but it's like a high recreational dose of ketamine. I just want you all to know that.
Ongeveer, dus hou daar ook rekening mee.
Oh,
Hoe voelt het?
brandt een beetje.
Ja?
Ja. Ik heb geen smaak in mijn mond of zo van interessant. Maar ik moet wel echt in mijn neus zitten nu.
He'll have taste in his mouth.
Dan gaan we even wachten.
Ja.
Het kan heel snel gaan, hè?
Ja.
Voel je al iets?
Nee, nog niet.
Nee?
Nee.
Dan gaan we even wachten. We zijn nu 20 minuten verder. En je voelt het al wel lekker, toch?
Ja, mijn zicht, dat is nu een beetje aan het golven. Zo. Zo. Oh, dit is vet raar, jongen. Maar het is wel echt vet. Nou, alles rekt uit soms zo. Dit is echt wel echt iets anders. Dit is echt wel iets... Je kan het niet met een druk vergelijken wat ik tot nu toe heb geprobeerd. Nee. Dit is echt heel... Het is echt... Ja. Het is echt vet raar.
Hoe voelt dat?
Ja, raar. Ik voel het niet.
En als ik erin knijp?
Nee, what the fuck? Nee, what the fuck?
Echt niet?
Nee.
Je vraagt je eigenlijk af, is dit nog wel mijn lichaam?
Ja, een beetje. Ja.
Daarom kan ketamine dus ook gevaarlijk zijn, omdat je dus heel weinig voelt. En daardoor kun je je verwonden zonder dat je het door hebt.
Personally know someone who headbanged on ketamine to the point of accidentally spraining their chest and not noticing until they'd come down. This being said, you have to be pretty fucking high for that to happen. You have to like anesthetize yourself. Because that's what it is. It's an anesthetic, right? And at recreational doses that are a bump, like enough powder to fit on the tip of a key, basically, that's called a key bump, you're not going to have that kind of a dissociated numb experience. It's not going to really happen. But if you get to higher doses, especially if you get close to what's called the K-hole, which we'll come back to in great detail, then you might actually run the risk of anesthetizing yourself. It's not that common that people actually get injured under the influence of dissociatives because they can't feel it, but it's not impossible, you know what I'm saying? It really is more dose dependent, I would say. So let's look at nitrous.
Wat in, uit. Haal heel even adem en daarna tot hij niet meer komt. Sommigen nemen het in 1 keer. Maar ik doe het gewoon net zo lang tot ik niet meer kan. En dan laat ik het ballonnetje flikkeren en dan zien we wel wat er gebeurt.
You should do nitrous sitting down if you're going to try and take a big hit of it. And I'll explain why when we get to that. If you're just hitting a balloon in like a couple of goes, it's not as big of a deal. But if you do what she does, you should probably sit so you don't fucking fall.
Ja, nou, ik wacht even de bel van. Ik kan je vertellen. Je kan het dus ook gewoon in één keer allemaal in je mond doen, want dan heb je wel hetzelfde. Leuk. Ja.
You don't always start laughing like that, let me tell you, but it only lasts for like a minute and a half to 2 minutes, I would say max, then maybe a little fuzziness afterwards.
Okay.
What's up? Someone say something? Okay, so for opioids, the naturally occurring opioid in your system that we'll talk about the most in this class is endorphins, which is this insane chemical structure, but there are a couple different kinds of endorphins. And these are the chemicals within your body that naturally produce your own defense from pain. And the way they do this is from blocking pain signals from being sent. So if you have more endorphins in your body, you're going to feel more bliss, or you're not necessarily bliss even, you're going to feel kind of like a sensation of being comfortable because there's nothing indicating that you feel pain, basically. And this is kind of a more nuanced high. Again, like, I guess I could say that all of them are nuanced highs. Drugs are nuanced, what can I say? But in terms of endorphins, they're just the closest comparison that I can make to exogenous opioids, right? So, and we'll get back to what exogenous means in a second. So if you activate an opioid receptor, an increased activation of opioid receptors, less pain, and also lowered respiration, breathing, lowered heart rate, lowered blood pressure, and lowered pain signaling. Oh, I hate that there are 2 spaces between these words. Ooh. So some examples of this might be Percocet or codeine or fentanyl, which I'm sure many of you are familiar with in some capacity right now. And morphine, and those are just kind of like the medically applicable ones. So just to clear up some terminology with this, an endogenous opioid or an endogenous chemical, endogenous anything, is something that's made inside of the body. An exogenous chemical, whatever, is something that's made outside of the body. So an example of an endogenous opioid would be endorphins. An example of an exogenous opioid would be heroin, something that you introduce into the body in order to mimic an effect of something that's already happening. So an opioid receptor will accept anything that binds to it that has the correct shape. So remember that exogenous and endogenous opioids look very similar to your brain. So you basically can just like activate that system using an outside drug. That's how that happens. So just to reiterate again, analgesia is pain relief. That's what that means. So if you see that something is an analgesic, that means that it's a pain relieving drug. And we don't like this terminology, and we'll come back to why.
And now meet Jason Amaral. He is the fed.
We met Jason on the street after he scored more drugs from friends.
I just did some heroin and I was sick. And I just did a shot and I'm very, very high. Like, and I feel great and I'm going to do what I need to do to make money. You know what I mean? And that's just how it is.
But Jason.
So a lot of the time, people that are under the influence of opioids, in this case it's heroin, but really it could be anything, are just kind of softened, like nodding in and out a little bit because their body is not only sedated from this, but also is blocking pain signaling. So in some cases, like this guy, Jason, he was dope sick and experiencing withdrawal, so he needed to do heroin in order to ensure that he could go about his day and function without feeling basically a lot of pain and discomfort. And for other people, it induces a state of nodding in and out or like blinking in and out of consciousness. Cannabinoids, very complex system in the brain, super hard for me to describe in this class, and everyone is always confused, so please make sure that you ask me if you're confused when we get to that section. Cannabinoids are basically the great moderators of the brain. Cannabinoids inside your body, because yes, I do mean to tell you that your brain has an entire weed system in it already. Cannabinoids inside of your body are responsible for regulating all kinds of functions. They regulate your sleep, your mood, your appetite, your sex drive, your hunger. I already said that, but the cannabinoids are just like, there's so much going on with them. and they're also pain relieving as well. So the general function of what they do is they regulate other neurotransmitters. They're responsible for being like, okay, well, this neurotransmitter, or like,
Please, stop.
What?
Oh. Oh my God, I'm sorry. I didn't realize I was on mute. I was yelling at my cat. Oh.
Has this happened before? Was that you that yelled at your cat last time too? Cats deserve to be yelled at sometimes.
I don't know. I don't think it was me because I wasn't at last class, but
well, whatever the case, I hope your cat gets its shit together. Also, I bet it's very cute. I wish I had a cat. So around here, cats live in the bushes, and they all hate you, except for one. So cannabinoid receptors, I'm going to skip that. Let's look at someone who's baked.
Hello. Again, Facebook. Pay no attention to the mess in the background. That's just stuff that's just back there. So, still bored, but I've come up with an idea to entertain myself and maybe other people. I'm gonna start can't even
That's the weed. So one more reminder is that endogenous refers to things that are produced inside of the brain or body. So in our case, we're going to be referring to neurotransmitters as the endogenous version of drugs. So if I asked, generally speaking to you all, what is the endogenous molecule pertaining to psychedelics? What's produced in the brain?
Serotonin.
Nice, very nice. Serotonin indeed. So psychedelics are drugs that are exogenous, right? They're produced outside of the body that influence an existing system inside the body for serotonin. So what's an endogenous molecule? The exogenous molecule for which is heroin. Something produced inside the body that is similar to what's produced outside the body, heroin.
Endorphins?
Endorphins, nice. So I know that I'd previously mentioned the difference between like psychedelics and MDMA, for instance, and that they both impact serotonin systems, and yet they have wildly different effects. So how do we draw the comparison between them, right? Like how do we identify the similar trends between them? And this is kind of similarly exemplified in something like Molly and Coke. Now, both Molly and Coke are considered to be stimulants, but very different ways, right? Like MDMA is not quite as stimulating as cocaine is, and they're both also serotonin agonists. So serotonin agonist, MDMA, serotonin agonist, cocaine. So how do we even tell these two things apart? Because they're both acting on the same system. And the answer to that is that MDMA is a massive serotonin agonist. It is a serotonin releasing agent. It dumps serotonin basically. And cocaine to a much smaller extent. It still does it, but that means that the effects profile of coke is going to include other things like norepinephrine and dopamine to give it the effects profile that it does. Oh, the person in the weed video, they didn't actually say anything. He just was like so baked that they just started like cracking up for the entire time. There was no actual thought attached to it. That's the idea. So MDMA, substantial release of stored serotonin, coke, some release of stored serotonin. So they're both stimulants and they both are serotonin releasers, but they only have like, they kind of pick and choose or pull the different like levels to which they impact both of those neurotransmitters. We don't have to look at that. So some of the ones that we've gone over so far are noradrenaline, otherwise known as norepinephrine, which is concentration and fight or flight. Then there's dopamine, which is reward and motor control. Serotonin is mood. Endorphins are for pain relief. Euphoria, I don't know if I agree with that very much. Glutamate is memory and connection, and then GABA is calming. if you need a summation. So there's a reason that in this I only brought up a couple of specific receptors, and we're not going to talk about it because that's too complicated for right now. Generally speaking, if a substance acts on GABA, glutamate, or norepinephrine, it is either speeding up or slowing down the system. If it acts on serotonin or dopamine, it alters your perception and your mood. If it acts on opioids, it produces pain relief and sedation. Does this kind of make sense to everybody? And then we have dissociative, or wait, no, what am I talking about? Yeah, so these are the major neurotransmitters and what they do. GABA, glutamate, norepinephrine, those three will either be speeding up or slowing down the system. Serotonin and dopamine are responsible for perception or mood. Opioid is pain relief and sedation. Okay. Next. Okay, previously on DrugsCo. What are the major neurotransmitters? Hit me with them.
Serotonin.
Serotonin? I wish I had a classroom. Major neurotransmitters. GABA, thank you.
Dopamine.
Dopamine.
Glutamate.
What did you say? Glutamate? Glutamate, yeah.
Norepinephrine.
Norepinephrine. One starts with a C. Think weed.
Cannabinoid.
Cannabinoids. And then one kind of if the other one is endorphins, but really we're just looking at the opioid system as a whole. Right, so we have dopamine, norepinephrine, GABA, serotonin, glutamate, endorphin/opioids, and cannabinoids. What is the opposite of an agonist?
Antagonist.
What is the opposite of inhibitory?
Excitatory.
Opposite of GABA? Do you remember what GABA does? GABA slows the system down.
Glutamate.
Nice, very nice. So remember, GABA is an inhibitory neurotransmitter, glutamate is an excitatory neurotransmitter. Now, a lot of people get confused by this and they're like, well, norepinephrine is an excitatory neurotransmitter because it activates fight or flight, but that's not what it's quite about. Inhibitory and excitatory are more about whether or not this neurotransmitter is facilitating communication between your brain and body or not. Norepinephrine simply stimulates your brain and body to get ready to go. I know that's a little bit flaky. What's the opposite of endogenous?
Exogenous.
Nice. Very nice. What kind of glutamate receptor do dissociatives act on? Anyone remember my song?
NMDA.
Yes. Oh my God, my heart sings. The NMDA. I don't even know if I'm doing the letters properly. I don't know how to make an N with my body. They didn't teach me that in primary school. What does it mean if something is a serotonin agonist? I know y'all know this.
Produces more serotonin?
It could produce more serotonin. I'm looking specifically for that it increases the effects of serotonin. And the reason that I'm nitpicky about it is because there are a couple different ways that it might increase the effects of serotonin, but that is one of them. That is right. And we'll go into today what those different ways are. What category of substances increases the effects of GABA?
Cough syrup?
Cough syrup. And what category does that belong to?
Dissociatives.
Cough syrup does belong to dissociatives, but also depressants. So when we're looking at GABA, that's why I kind of specify the difference between GABA and glutamate, because dissociatives are interesting in that they are decreasing the effects of a neurotransmitter that would typically connect your brain and body, whereas depressants are increasing the effects of a neurotransmitter that typically calms down your brain and body. So there is a difference to be made there, right? Like GABA will produce feelings of calm if there's more of it, whereas glutamate, if there's less of it, will just make you less connected between brain and body. Does that make sense? Any questions on that? So GABA agonists, substance that increases the effects of GABA, are depressants. A glutamate antagonist, so it decreases the effects of a connective neurotransmitter, is dissociatives. I know that's a little weird. We'll go over it over and over again, don't worry. Anyone know the medical term for when you lose oxygen to your extremities? It starts with an H.
Hypoxia.
Nice. And what category of substances might induce this if you really go balls to the wall with it? Anyone know this? Just guess.
Nitrous.
Nitrous. And what category is nitrous part of?
Dissociative.
It is a dissociative, but specifically with this one, I'm looking at the route of administration.
Inhalant.
Nice. There it is. So inhalants, because of sometimes there's unpredictable effects from inhalants. There's something called sudden sniffing death that can come in some, it's not very common, but it can happen from inhaling things like aerosols and spray paints and stuff like that. And with less medical inhalants, like nitrous, you have to put like a bag of nitrous over your head and really suck that shit if you want hypoxia to happen. But with other inhalants, there is a possibility of there being like sudden cardiac arrest, which causes a lack of blood flow to your extremities. But that is not super common. However, it's something to be aware of if you decide that you want to huff paint. You know, it's really just something to know. Skin picking and itching. What's the word for this one? I don't know why I'm so big on having people remember this word because it's really not that helpful. Starts with a P.
Pruritus.
Nice. Pruritus. And what two categories of drugs might induce itchiness?
Stimulants.
Okay. And what else? Any other
Opioids.
Opioids. Nice. Very nice. Okay. Now, analgesia. Oh, wait. I should have just asked. Well, that's fine. A lot of different categories of drugs can induce pain relief, right? Depressants can induce pain relief, although that's not quite as common. I think that's primarily because a lot of depressants have opioid-like qualities. Some inhalants can induce pain relief depending on the inhalant. Many dissociatives induce pain relief, and opioids in general induce pain relief. What is, oh, yeah, I didn't look at the animations for this one because I didn't think we'd get to it, but that's okay. What is this middle section here called? Between the presynaptic neuron and this thing, what is this middle section, this space called?
The synapse.
The synapse. I don't even know my own animations. That's okay, you're gonna roll with me, right? I don't have tenure. Okay, we have neurotransmitters in here. I didn't even label the fucking synapse. I don't even know, someone fire me, I swear to God. Okay, postsynaptic neuron right here, right? So we have presynaptic neuron that contains neurotransmitters. They're released from their bubbles called vesicles. They bind at receptors on the postsynaptic neuron, and this space is called the synapse, right? And these are the receptors right here. That was bad. I did bad. Okay, so what does an agonist do? A drug that is an agonist, what does it do?
Increases the effect of something.
Exactly, thank you. It increases the effects of a neurotransmitter. What does an antagonist do? Easy points here.
Decreases the effect.
Decreases the effect, right. Question is, with inhalants, does hypoxia only happen if you're doing it continuously, like putting your head in a bag of nitrous, or is it a risk if you do them frequently? It really does depend on how you're doing what inhalant. Many inhalants that are more off-market, like I said, like paint thinners and whiteout, are going to be more likely to induce hypoxia from sudden sniffing death, which is where your heart just kind of stops. The problem with inhalants as a category is that it, generally speaking, includes a certain set of effects that you feel. Like, for instance, whiteout and correction fluid is really popular among children, especially street children, because of sexual assault that happens on the streets, and also because of the necessity for going many long days without food. So inhalants generally as a class are capable of inducing these feelings of kind of like dissociation and pain reduction. And some of them are just simply more toxic than others and more likely to induce this in others. I would say, generally speaking, if you're doing something like nitrous, your risk of hypoxia is non-existent unless you're doing like a continuous stream of it without effective oxygenation, because really what you're looking for here is getting enough oxygen to your blood. That blue tinting implies that you don't get enough oxygen to your blood. So if you ever find someone that's unresponsive or unconscious, you should check their extremities to see if they have blue tinting, because that means that they're not getting enough oxygen flow. And that's a really good indicator that that person is not breathing effectively or that their heart isn't working effectively. So if you see someone with blue tinted extremities, start doing CPR. Don't worry about getting fentanyl on you. You're not going to fucking get sick from fentanyl on you. Ask me if you have questions about that. Antagonist decreases the effects of a neurotransmitter. Also, am I talking too fast for people? Because I watched a couple of these recap videos and was like, wow, I sound like I'm on 1.5x speed. Would anyone like to put in a request for me to talk slower?
Maybe just a hair.
Okay, I can talk a little bit slower. So in terms of agonists, we have multiple different ways that agonists can exert their effects. And that's why when someone said that agonists work by increasing the production of a neurotransmitter, that's one of them, but it's not the only way that they do so. So one of the ways that agonists function are by mimicry. They mimic an existing neurotransmitter. They look like the same shapes, they fit into the receptor and basically act as a substitute neurotransmitter. Another way is increasing production of that neurotransmitter. So instead of the drug itself going and binding in the receptor, it will go in and cause the neuron to produce more of the neurotransmitter so it can do its own thing. And this is part of the idea behind many kinds of antidepressants, is that they want to increase the production of a neurotransmitter. And then there's reuptake inhibition. Now, this one is a little bit more complicated, but the gist of it is that, actually, no, we'll come back to that in just a second. But know that these are the three main ways that agonists function, looking like the same thing as a neurotransmitter, so it can basically begin and do that neurotransmitter's job, releasing or producing a bunch of the neurotransmitter, or preventing reuptake, and we'll get to that in a second, right now. So let's think about an SSRI real quick, right? So an SSRI is a selective serotonin reuptake inhibitor. And what we're looking at right now is reuptake inhibitor. In any given neuron, right, we have presynaptic neuron here, postsynaptic neuron here. The synapse is the space between them. Neurotransmitters get released into the synapse. They bind on the postsynaptic neuron at the receptors, right? All of these things are here, neurotransmitters. And now we have these things, which are transporters. They're reuptake transporters. And what they do is basically electricity releases neurotransmitters, they bind, electricity continues, and then the neurotransmitters are like, fuck it, we're done, we're going home at the end of the day. So they get released from the receptors, they float back up, and these reuptake transporters act like little vacuums that suck them back up and recycle them, basically. It helps your brain not have to put quite as much effort into making more of them. So think about what a reuptake inhibitor would do, right? It would prevent this process of neurotransmitters getting sucked back up and repackaged, so that instead they just hang around in the synapse and continue binding, continue floating around and doing their thing. Now, the reason that we think this works in the case of SSRIs is that it basically increases the effectiveness of your existing neurotransmitters. So instead of them getting sucked back in and repackaging, it makes it seem like there's a lot more serotonin to go around because it will just keep binding repeatedly until it's eventually discarded, destroyed, sucked back in. Anyone have questions about reuptake? This is another thing that we'll come back to repeatedly. Now for antagonists, it's similar, but it's not quite the same. So kind of in the same way that an agonist might mimic an existing neurotransmitter and stick itself in the receptor and do that neurotransmitter's job for it by continuing the signal, an antagonist might block the receptor. It might stick itself in there and be like, this is my space, like Shia LaBeouf, you know? Or alternately, it might decrease the production of that neurotransmitter. You make less of that neurotransmitter, or destroy the ingredients to make them, or it might increase reuptake. So if it increases reuptake, this basically means that you're pulling neurotransmitters out of the synapse even faster than you would have before. So that means that there are fewer of those neurotransmitters available to bind and induce their effects. So just as a refresher on inhibition and excitation, inhibition, an inhibitory neurotransmitter, is something that reduces the overall level of activity in the system, right? So GABA is an inhibitory neurotransmitter. It reduces communication between your neurons. And glutamate is an excitatory neurotransmitter. So it excites the system. It increases communication within the system by increasing the strength of the signaling. So increasing the amount of electricity that's basically being allowed to pass through. That's glutamate. So inhibitory, GABA. Excitatory, glutamate. So if you reduce the activity of an excitatory neurotransmitter, you're going to be reducing your overall system's communication. Dissociatives. So again, inhibition slows or stops the electricity from going through. So GABA will slow or stop the electricity from going through. You can think of it kind of like if someone is just like sitting there slamming an easy button over and over and over again, and their kind mother in an apron comes up next to them with a tray of cookies and puts their hand on yours and says, "Son, now is not the time." And that's GABA. It's your mom. Who would have known? My mom probably would not have done that. She would have freaking not done that. Excitation, on the other hand, is increasing the current flow of signaling, increasing the passage of electricity. So this is if someone is like, they're pressing their easy button and someone runs up next to them and is like that's glutamate, increasing the amount that electricity is going through. Okay, so GABA agonist, an example of this, means that GABA is increased, which means that GABA is inhibitory. Or sorry, which not means that, but that just is how it is. GABA is an inhibitory neurotransmitter. If a GABA agonist is introduced into the system and GABA is increased, what will that look like in the system? We have an inhibitory neurotransmitter. We introduce a GABA agonist, which increases the effects of GABA. So what does that look like in the system? I know it's all topsy-turvy. Take a minute to think about it.
Dissociation?
Not quite. Not quite. You're in the right ballpark, though. I know that it's very tempting to look at dissociatives as being a class that will specifically impact GABA. But interestingly enough, dissociatives are the opposite. They impact glutamate by reducing its activity. So something that increases GABA's activity is a depressant, right? Because remember, you can think of it this way. GABA, when it's released in your body, makes you feel less anxious. We can just put it like that for now. GABA in your body, you less anxious. Everybody happy, maybe, I don't know, but less anxiety in your body. So if you increase the effects of a neurotransmitter that makes you less anxious, then a good way to think about that might be a depressant effect on your system. You can think of benzos as a really good example of this because they're intended to be anti-anxiety. On the other hand, if you're looking at dissociatives, then you're looking at communication between your brain and your body being disrupted. So think about what each neurotransmitter does on a daily basis in your body. Remember that GABA is responsible for calming you down and making you feel relaxed, whereas glutamate is responsible for communication between your brain and your body. Does that make a little more sense? Maybe? Crickets. All right, well, we'll just move on. So GABA's inhibitory effects are increased by an agonist, which means that GABA will be inhibiting your system even more, which means that you'll be feeling more sedated, less anxious, more calm. And this is part of what gives depressants their powerful sociable effects and also their reinforcing effects, because they make people feel much more capable and confident of interacting in social situations because there's less pressure, because they feel less anxiety. So just one more recap of this. Dopamine is responsible for regulating what and what?
Rewards.
Okay, reward, and what else? Dopamine.
Motor control.
Very nice, motor control. A dopamine agonist increases or decreases the effects of dopamine?
Increases.
Very nice. And what does that mean that a person would feel? If you're increasing the effect of dopamine.
Confidence.
Confidence. And also, anything else?
Euphoric.
Control, I guess.
Motor control, sure. Well, I'm looking specifically at reward right here because I think the word euphoria, which I heard someone say, is something that a lot of people kind of broadly apply to different drugs. And while many drugs can make you feel euphoric, I want to really point out that a lot of what stimulants do isn't necessarily make you feel euphoric, but make you feel like what you're doing is more rewarding to you, like feels better to do, feels more valuable to do, feels more interesting and capable, basically. So if you're high as balls on Adderall and you go to a party, you're probably going to feel really good about everything that you're doing there. You're going to be like, yes, I'm doing a good job socializing. Yes, I'm doing a good job dancing right now. Yes, I look like hot shit right now because I'm doing such a good job at these things. That's probably like 60 milligrams of Adderall. But that's something that we should keep in mind here, is that it's not necessarily euphoria always. It's more nuanced than that. It's like euphoria you might feel if you're rolling, for instance. And in some cases you might feel, which is MDMA, in some cases you might feel euphoria from opioids, but generally you'll feel like kind of comfort and sedation. So I know that might seem a little nitpicky, but when we get into the more specifics of each of these drugs, we'll kind of see that the effects profiles of them, euphoria isn't actually quite that common. Like, we can feel euphoria on stimulants for sure, but when we're talking about what dopamine does in particular as a neurotransmitter, we want to talk about specifically the reward function of it, because that informs euphoria. So what's an example of a dopamine agonist? That's an interesting question. Let's find out. Dopamine agonist, what's an example? Come on, y'all. I know that you know this.
Psychedelics.
You're on the right track, but not quite. Think about dopamine feeling rewarded for things.
Stimulants.
Stimulants, that's right. So an example of dopamine might be meth, because that's a stimulant. I'm looking up the definition of euphoria, but all it's coming up is, what's her name? Is it Zendaya? There's no definition for euphoria. It's just the TV show. So a dopamine agonist will increase the effect of dopamine. And one such example of that is meth. But there are also other examples like cocaine and amphetamine. And that's stimulants, right? Oh shit, I'm over time. I'm so sorry. I did not even notice. Get me out of here. Thank you guys for popping into DrugsCo. I will see you next Tuesday.
Thanks, Rachel.
Thank you.
Have a
Bye.
great night, you guys.
Thanks.
Bye.